Today we are solving LeetCode 1415, the kth lexicographical string of all happy strings of length n. Before we get into the actual problem, let's start with a short analogy. If you'd prefer to skip it, you can move to the next timestamp where we begin the problem directly. Imagine a commander arranging 3 types of squads in a line. The only rule is that the same squad cannot stand next to itself. Now someone asks for the kth formation in alphabetical order. Instead of listing every possible formation, the commander realizes that each starting choice leads to the same number of formations, so he can skip entire groups and jump directly to the correct one. That is exactly the strategy used in this algorithm. Now moving to the actual problem, we must generate what is called a happy string. A happy string follows 2 rules. First, the characters can only come from the set A, B, C. Second, no 2 adjacent characters can be the same. Our goal is to return the kth happy string in lexicographical order that has length n. If the total number of happy strings is smaller than k, we simply return an empty string. Now, when reading the question, a few signals immediately stand out. On my website, I summarize this using pattern recognition signals. First, we are building a string character by character with a constraint on adjacent characters. That is a classic sign of backtracking or DFS generation. Second, the question asks for the kth result in lexicographic order. This usually means either generating everything in indexing or rank decoding mathematically. Third, the alphabet size is very small, only 3 characters. Because adjacent characters cannot repeat, every position after the first has exactly 2 valid choices. Fourth, the constraints are small. N is at most 10 and K is at most 100. The total number of possible happy strings is therefore at most 1,536, which means brute force generation is perfectly feasible. And finally, keywords like lexicographical order, kth, and adjacent characters must differ strongly point toward either backtracking generation or mathematical rank decoding. Now let's understand the underlying concept. First, we calculate the total number of happy strings of length n. The formula is 3 multiplied by 2 raised to the power n minus 1. Why? The first character has 3 choices, A, B, or C. After that, every position has exactly 2 valid choices because it cannot match the previous character. So the total count becomes 3 times 2 to the power n minus 1. If k is greater than this total, then the answer does not exist and we immediately return an empty string. Next comes the key idea used for fast decoding. At any position pose, each valid character leads to the same number of complete strings underneath it. That number is 2 raised to the power remaining length, which is 2 raised to the power n minus pos minus 1. We call this value the branch size. This tells us how many strings lie under each possible prefix. Using this, we can skip entire subtrees without generating them. Now let's walk through an example. Suppose n equals 3k equals 9. First, compute the total number of happy strings. 3 multiplied by 2 squared equals 12. Since 12 is greater than 9, the answer exists. Next, we convert k to 0-based indexing. So we subtract 1, k becomes 8. Now we start decoding the string 1 position at a time. Position 0, the remaining length is 2. So the branch size becomes 2 raised to the power 2, which equals 4. The valid choices are A, B, C. Each of these prefixes covers 4 strings. A covers indices 0 to 3, B covers 4 to 7, C covers 8 to 11. Since k equals 8, it falls inside the C group. So we pick C. The result becomes C. Now update k. K becomes 8 modulo 4, which equals 0. Position 1. The remaining length is 1, so the branch size becomes 2. We cannot repeat the previous character, which is C. So the valid choices are A and B. These prefixes cover CA indices 0 to 1, CB indices 2 to 3. Since k equals 0, we choose A. The result becomes CAK stays 0. Position 2. The remaining length is 0, so the branch size becomes 1. We cannot repeat A, so the choices are B and C. Their indices are SAB 0, CAC 1. Since k equals 0, we choose B. The final string becomes CAB. And if we list all happy strings of length 3 in order, CAB is indeed the 9th one. The important point here is that we found the answer in only 3 steps without generating all 12 strings. Now let's briefly look at the code. There are actually 2 common approaches. The first approach uses backtracking. We perform a DFS that builds the string character by character. At each step, we try characters A, B, C, skipping the one that matches the previous character. Because we iterate in sorted order, the generated strings automatically appear in lexicographic order. We collect them in a list and return the kth element if it exists. The second approach uses the math decoding trick we just walked through. First, we compute the total number of happy strings. If k is too large, we return an empty string. Then we convert k to zero-based indexing. Next, we iterate through the positions of the string. At each step, we compute the branch size, determine the valid character choices, and pick the correct branch using integer division. Then we reduce k using modulo so it represents the index inside that branch. After repeating this for all positions, we join the characters to form the final string. Finally, let's talk about complexity. For the backtracking approach, we generate all possible happy strings. The total number is 3 times 2 to the power n minus 1, so the time complexity is O(n)(i)(2)(o)n. But since n is at most 10, this is still extremely fast. The space complexity is also O(n)(2)(n) because we store the generated strings. For the math decoding approach, we only loop through the string positions once, so the time complexity becomes O(n). The space complexity is also O(n) because we only store the resulting string. And that's the complete idea behind this problem. Thanks for watching. If this helped, consider liking, commenting, subscribing, and sharing. For more problems explained like this, check out the playlist linked in the description.